Welcome everyone to the first lecture of our new course, Deep Learning for Natural Language Processing. So I'm Phil Blunsom. I'm a lecturer here in the Computer Science Department, although I spend most of my time at a company called DeepMind in London, 4 days a week there. And this course will be a collaboration between the Computer Science Department and DeepMind, and so we've got for you a range of different speakers, mostly from DeepMind and a few other places that you'll get to meet during the course of this lecture. So let's get started. So the sort of first starting slide is, why should you be here and take this course? And the key reason you should take this course is because you're interested in language. This course is going to be about language. It's going to be about the computational processing of language and how it relates to artificial intelligence. Artificial intelligence is a pretty hot topic at the moment in computer science and society in general. And hopefully by the end of this, you'll agree with me that language is really one of the most compelling aspects of intelligence worthy of our study. So historically, language, computational linguistics has been very strongly associated with AI. Maybe some would say too much so. So through the second half of the 20th century, a lot of work in AI was language-based. Not a whole lot of progress was made. People moved away from language. Recently, quite a lot of progress has been made. And now people are coming back to this problem of how do we deal with intelligence and language. Language is cool because it's how we communicate, but it's more than just communication. So we shouldn't just simplistically think of language as a way of conveying ideas between us, but we can think of it as a way of evoking concepts in people we speak to. So if I say the word dog, that's just a sound wave, but now all of you, I've invoked the concept of a dog, a sort of four-legged furry creature, in your minds. And you all have slightly different concepts of dog, but just by using the medium of language, I can invoke that concept in you. So language is more than communication. It's an interesting phenomena. It's one we still don't really understand that well. So that's why there's research on how to process language, as we'll see in this course, but also we don't fully understand how humans learn language, how children come to be so proficient in language so quickly with so little stimulus. Okay, so hopefully that's a bit of high-level motivation. So some nitty-gritty details about this course. There is a web page. I don't think there's anything much interesting on it yet. Maybe there will be later on. We'll see. These lectures are being recorded. Depending on how difficult it proves to be, hopefully I'll be able to put them up so that you can review them. But it may take me more time than I might hope to do that. There's no textbook for this course, partly because a lot of the things we'll discuss are quite new, and most of the things, especially the second half of the course, relates to research really done in the last 2 or 3 years. But there are some good general texts. So there's a very new textbook on deep learning from Ian Goodfellow and Joshua Bengio et al. Called Deep Learning. You can get that in physical form, or the website has the PDFs that you can download. So that's a very useful resource. It covers deep learning in general. There's chapters that are quite relevant, particularly the recurrent neural network chapter, which could be quite useful to you. And then there's lots of textbooks in general on machine learning. So particularly the Murphy textbook, Machine Learning. I've left off the author there, but that's Murphy, and the Bishop textbook. You'll find those in the library because I think I've used them in the past for machine learning courses. So they may be in your college libraries. Obviously the lectures, one is on Tuesday at 4 till 6 and the other on Thursday, also from 4 till 6. Slightly different to other courses in CS. I've allocated 2 hours for the lectures. That doesn't mean all the lectures are going to go for 2 hours, but I just thought I'd allocate plenty of time. I find 1 hour a bit too short sometimes. We're going to have lots of invited speakers. Some of the weeks we might put sort of 2 hour-long lectures back to back in one of the slots. On other weeks, they might be quite short. I'll try and let you know beforehand roughly what's happening. In this first week, we'll probably use most of the 2 hours today and on Thursday. So there will be no lectures next week. So most of the people involved in the course are away in Germany on a seminar next week, so there's going to be no lectures. There will, however, be practicals next week. So don't forget that. So there's going to be 7 practical sessions. I think they're on Mondays and Fridays, but you should check the timetable. You've got some excellent demonstrators in Brendan, Janis and Yishu, all graduate students here in the department and experienced deep learning practitioners. So they should be very handy for you learning the practical aspects of the course. So there should be 7 of those from weeks 2 to 8. And finally, the assessment will be a take-home exam of the form that hopefully, well, MSc students amongst you are familiar with from last term. Okay, so practical details. Rough lecture schedule. So I make no promises that I will keep to this or that these will be the people giving the lectures, but roughly what we're going to do is today, after my short introduction, I'll introduce Wang Ling from DeepMind, who's going to give you an introduction to, or hopefully a review of basic machine learning and neural networks, starting from first principles, how to count, up to the backpropagation algorithm. And then on Thursday, Ed Greffenstedt will talk about lexical semantics. I may also have, I think Chris Dyer is going to come up as well and maybe talk a little bit about what we hope to do in the practical sessions. As I said, week 2, no lectures, so don't show up next week. Week 3, I'm going to talk about recurrent neural networks and language modeling, various issues involved in those, how to make them go fast. Then after that, we're going to run through lots of applications of these models. I won't go through them all here, but we'll have a range of guest lectures from DeepMind. Hopefully Jeremy from NVIDIA will come up and tell you a bit about GPUs, why GPUs are important for these sorts of models. GPU is a graphics processing unit, if you haven't come across that before. They happen to be the computational device of choice to run these models on. So hopefully we'll get a lecture from NVIDIA on those. And then, the second half of this course will largely look at applications of these models in translation and speech and language understanding. So prerequisites. So this is not meant to be an introduction to machine learning course. So hopefully you've all got some knowledge of machine learning. Otherwise you may find this a bit opaque. So at least you should understand, I've taken courses in linear algebra, calculus, probability. So the courses that undergraduates do here in their first year computer science degree are perfectly adequate. That is, what's covered in those courses adequate, maybe not what you remember from them. So if you can't remember that, review those ideas. We're not going to do anything particularly challenging in those areas, but basic ideas from those areas will be useful. So machine learning, as I said, this is not an introduction to machine learning course. It will be very useful if you've taken the introduction to machine learning course that was offered last term or last year here in the department or something equivalent. At the very least, you should have an idea of how to, what it means to train and evaluate a machine learning model, how to split up your training data and how to keep your test data separate from your training data and all these basic issues of machine learning so that you can actually work out whether your model works or not. You should know what overfitting, generalization, and regularization mean. That's very important. Machine learning is all about generalization. That's the whole point. How to generalize from what we see in the past to what's going to happen in the future. Optimization. So you should have a knowledge of what gradient descent is, stochastic gradient descent. Hopefully its various variants like Adagrad and such things. Hopefully you've come across these. If not, some reviewing will be in order. And also basic algorithms like linear regression, classification, and definitely a little bit of neural networks and backpropagation. Wang will go through those today, but hopefully that will be a review for you rather than an introduction. Finally, for the practicals, so in the practicals you'll be implementing these models, so you're going to need to know how to program. We're not going to teach you to program. We're not going to tell you what language or toolkit to use for those practicals, so it's up to you what you want to do. I've listed some here that are popular, so Torch, TensorFlow, Theano and Dynet. These are all good toolkits for implementing neural network models. Torch uses Lua as a programming language. The others are Python-based or C++, so you should choose something that you're comfortable with and make use of that. you're not going to be given a lot of help in learning to program or learning those toolkits, so you should be confident in being able to pick up those things. Okay. So going back to the course in general, this course is about, from the name, you can guess, deep learning for natural language processing. There's a lot more to natural language processing and computational linguistics and deep learning, so that this is not a comprehensive course in computational linguistics. You shouldn't come out the end of this course thinking that deep learning is the answer to all problems in language, or that we're going to get to AI simply by building bigger and bigger recurrent neural networks. This course is really about looking at recent developments in deep learning and language and some particular successes where these models are very effective. There's lots of things or areas where they're not effective, so this is just a caveat to start with to not feel that this is all there is to know about machine learning and language, and also language in particular. In terms of where we're at with AI and language, we're still very much scratching the surface of the phenomena that is language. We're a long way from real conceptual reasoning about language. And so whether the techniques that we'll discuss in this course will get us there is an open question. But you should have an open mind about these areas and not feel that while these techniques have impressive results, they're not the only way of approaching things. So we have a brief review of some of the things that we might look at in this course, hopefully to stimulate some interest. So language understanding is a core problem that we want to solve in language processing. So we want models that can hear or read text and understand what is being said. One way of testing understanding is to ask questions. So a classic problem in language understanding is what's called reading comprehension. So later on in the course, we'll discuss reading comprehension models. This particular example is from a data set we created at DeepMind, where we took news articles, this one from the CNN about Jeremy Clarkson punching his executive producer, and then ask questions of them and train models to try and answer these questions. If you look at this particular question, it's asking who will not press charges against Jeremy Clarkson. If you look at the article, to answer this question, the model needs to be able to stitch together a few different bits of information. It needs to understand from the opening sentence that it was a producer who will not press charges, and then later on in the article, the producer is actually named as Oysen Taiman. So a model needs to be able to put those things together and understand that there's a first event of the assault, and then the second event of the naming of the producer, and be able to put these bits of information together. So it's a cool and challenging task, and it's one that we're a long way from doing perfectly, but we have some models that can do respectively on such tasks. So we'll look at those. One of the areas where deep learning has had a lot of success in language is in what we call transduction tasks. So any task where you're trying to take a structure, usually a sequence, and convert it into another structure, normally another sequence. So a classic example is a speech recognition. In speech recognition, you get a sequence of audio signals, and you want to transduce that into the actual text that was spoken. Machine translation is also another classic transduction task where you get a sequence of symbols in one language, in this case French, and you want to transduce that into the equivalent sequence in English. If you put these together, you can do things like speech-to-speech translation. And if you go to apps like Google Translate on the web now, you can speak to them. They will try and convert that audio signal into text. They'll try and translate that text into another language for you and then speak that back to you. So up until a few years ago, all these problems were done with certain models. In the last couple of years, all of these industrial systems have moved to deep learning models, actually big recurrent neural networks. So speech recognition, machine translation are all done with big recurrent networks now, and text-to-speech as well is moving in that direction. So we'll cover these in the course over a couple of weeks. Another fun sort of task that we'll look at later on, it's become popular, is image understanding. So one of the great things about deep learning as an approach to processing language is it's the same approach that we use for processing images now. So deep learning has had a lot of success in image recognition, object recognition, and classification. And because we're now using the same models for processing images as we're using for language, it becomes very easy to put them together. So now it's straightforward to take a model that recognizes objects in images and stick that together with a language model that generates language, train these together, and we can train models to caption images if we have examples of images and their captions. And we can also train models to answer questions about images. So this is a data set that was produced for a task called visual question answering, where we have lots of images and questions about those images, what's happening. So from straightforward questions that a classifier might get right, like what is the man holding, to more inferential problems like does this man have 20/20 vision. Obviously there a model needs to understand something about vision being related to the glasses he's wearing, and that being an indication that he probably doesn't have 20/20 vision. So by this, one of the real contributions of the move to deep learning and language processing has been the ability to bolt together systems from vision and other modalities very simply and get these sort of models. So we're not going to deal too much with linguistic structure. The sorts of things that deep learning does well in language at the moment is still very much at the sort of behaviorism end of the spectrum, that is mapping inputs to outputs. So we're a long way from any sort of conceptual reasoning about things. And in this course, we'll mostly stay low level and look at sort of how do we transduce an audio signal into the text that goes along with that, or a French sentence into an English sentence. But you should never forget there's a lot more to language than just these shallow aspects. So here are some classic examples of a sort of random selection of language phenomena that we should not forget when trying to process language. So the first one there is classic sense ambiguity. So I saw her duck. Is it ducking as in the physical motion, or the bird? We've got idioms. So one of the wonderful things about language is its compositionality. So language follows what looks like sort of logical rules about how we can compose the words to get the meaning of a sentence. So he kicked the goal. The composition is basically the same as he kicked the ball. We're just changing the noun phrases there. But it doesn't always work. So in the classic idiom of he kicked the bucket, of course, that doesn't mean anything about kicking or buckets. It means he died. So language is compositional, except when it's not. And this is one of the most challenging things for any computational models. It's easy to write logical systems that process the simple examples, but as soon as you let that loose in the wild, someone will say something that doesn't fit your logical rules, and you'll have to deal with this sort of thing. So at the end of the course, we'll touch a bit on these issues and how we start to think about the sort of hierarchical structure we see in language. The final example there is something called a Winograd schema, which are these reference problems where if you read that sentence with the two alternate endings, so the ball did not fit in the box because it was too big or because it was too small, if you switch big and small, it switches what the it refers to. So if it was too big, then it's the ball which was too big. If it was too small, then it's the box which was too small. So getting your computational model to be able to tell the difference between those two is very difficult, because it has to have a notion of the physical world, of boxes and balls and size and how they could fit within each other. So that's one of the really hard challenges in language processing that we're a long way from solving, but we'll talk a bit about these sort of reference problems later on in the course. Okay, so that's my sort of introduction and motivational opening. So the rest of this lecture I'm going to hand over to Wang Ling, who's going to give you a thorough review of how to count and add numbers, and maybe a bit about neural networks as well, with the aid of some Sesame Street characters.